Okay, today we're gonna solve the energy equation with the spin transfer torque. So we already mentioned that we can handle the problem around the stable condition. We can take the kind of linear approximation by assuming the magnetic moment, mainly they pointing the original direction, which one is the stable condition, and there is a small perturbation because of the external perturbation. The external perturbation can be external magnetic field, or in our case, spin tensor torque, or any kind of external perturbation can be handled this idea. So this one is fixed one in this problem. Oops. Okay. So this is no time dependent. It's constant. 왜 이런지 모르겠네. It's constant, and only this small term is time dependent. So this small time dependent, we assume harmonic motion because we assume the perturbation can be described by the harmonic perturbation. Actually, any kind of the perturbation can be described by the Fourier transform of the harmonic motion. So once we can obtain the harmonic motion response, we can apply the Fourier transform for our solution also. So let's assume there is some homogeneous perturbation with frequency of omega. And it is natural, the magnetic moment, mx and my, which one is very small motion around the ground state, can be described by these harmonics with a different phase. And basically, this is kind of the understanding of the susceptibility, which one is response function. And you can find the response of the m as a function of the h. Here, this is the linear solution. So the motion of m is linearly proportional to the hx or hy, depends on this coefficient. But as you already know, in certain frequency, this frequency, the response getting very large. That's what we call the resonance. That's most important. And they represent the property of the system. And also, with this idea, what you can do is, we can find some instability condition, which means this susceptibility getting large, and sometimes getting go to infinite. So we already assume this mx, mi very small. That's the assumption of linearity, linear approximation. But if this is going to large number, means this value is getting large. So our initial condition is no more correct. So means the system is no more stable. So it's unstable. So they try to find a new ground state. So that's the possibility of the switching. Okay. So finding instability is related to the switching. That was very similar when we saw the Storm-Haas model. Actually, such kind of approach can be applied to any kind of physical system. If you describe the ground state, and if you have some small perturbation, and if they have such certain harmonic motion, it's still stable, but they are moving around the ground state. But if your perturbation matches certain condition, then the system is no more stable. So they try to find a new stable condition. That's the phase change or the switching of the system. You can apply to any kind of system of this idea. So now we will apply this kind of idea for the field switching or spin tensor torque switching. So let's start to assume any certain uniaxial magnetic substance with the ellipsoidal shape. The reason is usually we play with the films or certain nanopillar structure, but they can be modeled by this ellipsoid model with the proper demagnetization condition, demagnetization factors. So let's assume the magnetic moment initially pointing the z direction. That's why we assume the such a magnetism is pointing the z direction, and they have only xy component. Okay. So let's start the LLGcation with the spin transfer torque. And as we said, the m can be described by this linear motion, and small m, here we have this form. But the difference is we assume the exponential term by exponential I, instead of exponential I omega t, you can replace by just kt. So you can easily find the k is equal to the omega I omega is just harmonic motion. But generally here, this k is the complex number. So it can be I omega or certain real number. So just imagine that the k is the harmonic, the complex number. And for the simplicity, we assume the polarizer magnetism direction is the pointing the z direction. And now we have a H effective field of the external field term and the Dmax energy term. If you have a ionospheric energy, we can add up the ionospheric field in this equation. But for the simplicity, we have for the z direction, we have an external field and the Dmax field. And also we have a xy component of the effective field, total effective field, which is proportional to the Dmax coefficient of the x component and the magnitude of the mx. This is the magnetic moment of the mx component, my component, and this is the Dmax coefficient. So this Dmax coefficient represents the dimension field of each component. Okay, so remember that the HD is tensor of the so if we have a diagonal element of the diagonal element of the Dmax field, the HD can be represented by the tensor equation. So this, if this is diagonal, each HD coefficient proportional to the each component of M. So we have this Dmax terms. So let's think about the time derivative of the magnetic moment. Because this term is time constant with respect to the time. So when you take the derivative, this term is dropped. So we only have a small m dependence. And this guy has an exponential kt. So when you take in the derivative, we have a k at the front. And this part is nothing else but same to the m. So the ddt replaced by just k. We may find such kind of approach in many differential equation. Okay. This is the what we obtained this first term. And let's think about this precessional term. For this precessional term, we substitute this m and h here. Here is the m, and this is the h. It looks very long, and there are many components. We have a gxy and gxy in both sides. But we have a cross product. So it looks complicated, but you can do it step by step. So let's think about that first term. When you multiply with this g component with this one, the g component will be disappeared because the cross product between the parallel vector will be 0. So only this term survive. This is what we wrote down here. And we multiply the k, the g with x and y. We have a minus y and x. So this is the first term. Okay. And if you think about the then multiplication with this g, we have this component. So we multiply g with x and y, we got the y and z with the proper sign. Okay. And how about the multiplication of these guys and these guys? Here, I use this symbol, means the approximation, not the exact one. Why? Because this guy, we assume the small. So for multiplication of these two terms, we obtain the second order of the small m. And we already said we are interested only in the linear term. So we can drop the multiplication of these two terms. So now this is the first order approximation for the precession term. Okay. And we need the damping coefficient. We have to calculate this term. So we calculate this m cross dmdt. So we already said the dmdt has only the linear to the small m, and m has a sum of the large m with the small m, but the small m term can be dropped because of the linear approximation. So what you obtain is this component, because we multiply m means we have a mg term. So we change the mx to my, the y to the x by the cross product between them. Yeah. And how about the Chon-Yeol spin transfer term? We have a triple cross product, and we already assume the MP is the only g direction. So this large M, the MS term, can be dropped by this one. So we have this linear term, and this is quite similar to the previous one, but the vector term is a little bit different. But finally, you can obtain this result. Okay, I believe you can do it by yourself. Maybe you made some mistake, but basically you can understand what's going on here. So let's getting together all this calculation. This is from DMDT, this is precession term, and this is also precession term, and this is damping term, this is the STT term. So this LH equation now can write down with this linear differential equation. It looks complicated, but please remember that we already know everything except the small m and k. We're gonna solve this differential equation to finding the k or the small mmx is corresponding kind of eigenvalue and eigenvector. Okay, so it looks like some actually two simultaneous differential equations, but you can write down this one in a matrix form more simply by getting together by this k change to 2 by 2 matrix form. This is exactly this one, and we can write down here the x and y are mixed, so we can making the proper order. So we can make off-diagonal element term in a matrix form, and all m0x, my, m0x, m0y are same order. So we can collect all together. So we can make okay. So this equation, can see the important point is here. This guy is x0, 0x and 0y is opposite order. So this term contributes the open element. And this term contributes also open element. And this guy has a 0x, 0y, so they have a diagonal element. And all these guys are same. So we can write down all together by the linear, the diagonal term and open element term together. So once we collect, we obtain such matrix equation. Okay. So I believe all students in this room are very familiar with solve this kind of differential equations. Actually, this is the two coupled first order differential equation, but it's mathematically you can change it to coupled second order differential equation. To uncoupled, sorry. So means we can represent the mx2 as a function of my. Then it's only the the second order differential equation for the mx, and you can make the another second order differential equation for the my. Okay. Anyway, so what's the meaning of this differential equation? If we put the 0 for m0x, my0, m0y, they satisfy this equation because the right-hand side is 0. That is what we call the trivial solution. And we don't need to pay attention to the trivial solution. It's really trivial. Okay. Then what's the solution, the condition for the, we can obtain the non-trivial solution? If we have a inverse matrix of this matrix, we can multiply the inverse matrix in both sides. We got only the trivial solution. So this matrix must be singular. They cannot have the inverse matrix. So that means the determinant of this matrix must be 0. So let's find the determinant. Multiply these two diagonal terms here and minus multiplication of this one. So these guys came here, these guys came here, but we have a minus sign, so we can turn this is plus. So now we have this form. Okay, so this still looks very busy, but I hope students can following. Okay, now we are here. And the goal of this treatment is finding the proper value of K, which one is related to the physical response frequency. So look at this. This is the nothing yet. It looks very complicated, but this is the quadratic equation of the K. We have a K square term here, and we have K. This is the linear to the K. So actually we got a quadratic term only this separation. So we have a K square, and this term generate alpha square K. So we got the quadratic term. Okay. And how about the linear term? Linear term came from here and multiplication of this guy and this guy. So we collect the gamma in outside of the equation. Then this one came from here, and this guy came from here and here. Okay, this is the linear to the K. And finally, we need the constant term here. The constant term came from only this square of this one and multiplication of this guy and this guy. Okay, so this guy is to here and multiplication of these two guys is you can write down here. It looks complicated, but it's just quadratification for the K. You did this kind of you solved this kind of a quadratification maybe more than 100 times when you was high school student, right? So we can using the well-known equations, but before that, we can make some definition of new kind of effective field. Let's say HY0, HX0 by the blue and red. And this is H external minus with combination of the Dirac field for Gy, Gx. So that's why I put the X here and Y here, because we think about the Dirac field. So we can write down this above equation with this definition. It looks more simple, much simpler. And the general solution of this coordinate equation of K is here. From here to here, you can, using the well-known equation for the root, the second quadrant equation. Okay, so still it looks very, very complicated. So what we have to do is, please keep in mind, we are playing with the linear term, the linear approximation. And what you can do is, we know the alpha, which was damping constant of the ferromagnetic system. Usually the alpha value is very small. They usually order of 0.01 something. Yeah, in some special case, alpha is not small, but most generally, alpha is very, very small. So let's assume the alpha is small. So we can drop the square term of the alpha here, and here we can drop it. And also the AJ represent the spin transfer torque coefficient, and they are usually not that large. So we can drop it also, the second order. So this equation obtained more simple form here, because we can drop alpha here. We got the only gamma at the front, and here we can, if we drop alpha square, we have this term here really, and this term can be here because when you expand this one, we have also alpha square term, so we can drop the alpha square term. So we got this equation. Okay, we are getting close. Okay, so look at this equation. And even we can sometimes ignore this term also. So we can take the final approximation here. And please remember that the K values came from the exponential KT terms, which one is govern the motion of the M. Please remember that. And as I said, when I starting, K value is the complex number. And look at this. This guy, this one depends on its side. This is the real part of the system, and this is the okay. Let me focus this part first. This Hy0, Hx0 is kind of the field. And what's the physical meaning of the multiplication of these two fields and taking the root? This is nothing else but a geometrical average of these two fields. So this is the also field. Multiplication of two fields and taking the root, the dimension is field, and the physical meaning is the geometrical average of these two fields. And if you already know, if we multiply gamma with some field, we obtain the omega, is frequency unit. And because of this minus sign, we have this form. So what's the meaning of if we have an exponential term with I omega t? That's the oscillation, right? So this is the frequency of the oscillation for the described by this field term. So this oscillation frequency, it solely depends on the magnitude of these two effective fields. And this effective field is related to the external field and the Dirac field in this simple case. In reality, they should involve the analytic field and exchange field and so on. But anyway, the physical meaning of this term is not changed. This resonance, actually the frequency of the oscillation of the M solely depends on geometrical average of two fields. Which one is pointing x and y? X and y. Okay. So I'm going to explain what's the physical meaning of this one later. So we understand what's the physical meaning of this imaginary part. Okay. And what's the meaning of the first part? This part is the real number. Now, and in the sense of the effective field, what's the meaning of this term? Compared to this one, this is what we call the geometrical average. What's the meaning of this one? This is the normal average value, right? In Korean word, 산술평균. Okay, so do these two, okay, and if we multiply gamma with this term, they generate another frequency. And we multiply alpha. So this term generate frequency and multiply the alpha means actually we will gonna multiply t here in an exponential term here. So this term governs the damping of the system. So this is the kind of damping frequency or the damping time. Okay. So please remember that M can be described by this form, and the HY, HX has this form, and K now have this form. Okay. So simply say if we don't have any damping, let's say this is going to 0, then also if we ignore the STT, only the imaginary part survive, then the M is just preset with this frequency. And also this M, the omega resonance is multiplication of HY0, HX0. And actually in the infinite case, only NY is 1 and NX and Y is 0, NG is only 1. Okay. So this is only 1. Sorry, this geometry, sorry, we talking about this kind of geometry. So if we assume the infinite magnetic moment, the NG is 0, and here this is the, let's say, XY, then NX is only non-zero. NX is 1, NY and NG is 0. So let's do it here. This guy is 0, this guy is 0, this is only 1, this is 0. So we have a HX for this first term and HX minus plus MS for the second term. So this is the pulsation frequencies with no damping and no STT. Okay. If we have only damping without STT, we have a damped oscillation motion. And look at this. The MT can be described by this rotating the precession term with exponential T over tau. Here the tau is this term with the minus sign. With the minus sign. So the real part of this exponential term is negative. So they are going to 0. So that means the damping, right? So generally, this damping frequency is average of the hx0, hy0. And generally, these two precession precession frequency and the damping frequency are not the same. Sometimes they are same, and they are very similar number because one is the geometrical average, the other one is just the average. So this number is sometimes they are same, but generally not the same, but same order of magnitude. So actually, there are many experimental paper handle the finding the damping constant, but in many paper made some serious mistake. They confuse the definition of the damping frequency and the resonance frequency. They are not the same actually. Okay. Anyway, so now we discuss about the physical meaning of K when the STT is 0. Okay. So this is the I'm going to show this one later. Okay. So now let's focus on here again. And we already done the physical meaning of this one. It's damping. And we already done spin transfer torque act as a anti-damping. It's the reverse of the damping. So you can see here, if we have a large AJ, then damping will be suppressed because we have a large number, the small number, because this is the related damping. So this acting as the opposite way. So what happens if the real part of K become positive? So far, if we ignore the STT, this term always negative. So the system always damping. But if K become a net positive, what's going on? What can be happen? So please remember that we are talking about this situation. And if this is the real parts number, what happens here? It's going to infinite. So they means this system is no more stable, it's unstable. So that's what we want to find. So that condition, the real part of K become a positive is the plus G axis is no longer stable and our initial assumption is become incorrect. So we need a new stable condition. That is the switching. Okay. So finding this condition, the K value, the real part of K value is become positive is, let's back to definition of hy0, hx0 again, we can find this condition. Okay. And if you insert this is 0, this is 0, this is 1, then we can find, and also AJ has this form. I hope you remember that. We can convert AJ with the current density with some material parameters. And this term came from here. And this term can be simplified this one. So with this current density, the K, real part of K become positive. And STT getting larger than the damping of the system and started switching. Okay. So that is called the critical current density for STT switching. Okay, that is our conclusion. Actually, this approach tells us many important things. Okay, so the JC for the in-plane magnetic moment case, we have this form for the simplicity. But for the PMA material, we have a kind of effective field for the film normal direction. So if you do same calculation, we obtain this form, and actually they have this kind of critical current density, and this number is almost the same here. only difference is H external plus half of the MS. But in this case, the MS has a minus sign here. So the switching current of the PMA, because the switching current of PMA is usually smaller than the IMA case. So that's why, STT application of the PMA, the perpendicular magnetic moment, is important. Okay. And why the STT for the PMA is much easier? Look at this. For this, the in-plane magnetic moment, for the switching, we need to switch the magnetism to opposite direction. And what is the possible current source, the path of the magnetic moment? From here to here, we need to change the magnetic moment, not only the in-plane direction, but they should make some the perpendicular component. That's why it came from here. This is the perpendicular component. So they always give a positive effect for the current density. That means the magnetic moment is pointing in direction and switching to this direction. Maybe you can easily think from just rotating this one, but by nature of the STT, they should make such kind of large motion of outer plane. So they generate a lot of dynamic field, they require more energy. But for the PMA case, from here to downside, they need also pass through the in-plane. But in this case, the magnetic moment, the dynamic field is helpful to write down the magnetic moment in the in-plane. So for the IMA case, the dynamic field is against to the STT motion, while the dynamic field is helpful for the STT motion in the PMA. So dynamic field helpful switching in the PMA, while it acts as a barrier for the IMA. Okay. So generally, PMA requires smaller current density for the switching. Okay. And this is the result of the simulation with the STT. For example, if we apply the certain number of current density, which is small, then as you said, it shows the damped harmonic oscillation, right? And if you increase the current density to be more, they start to increase this magnitude. And if we increase more and more, it's more easily increased. And finally, they're gonna change their direction. Okay. Okay, here, I need talk about more about the critical current density or critical current. Yeah, critical current density, that is the important for the physics. It's important in a physical application. We already know the critical current density as a function of the certain material parameters. But in a real circuit design or real MNM application, current density is important, but also current is more important sometimes. So let's think about the current. From here, we can convert from current density to current by multiplying the area A, the cross-section area A. And if you multiply KBT in both sides, the denominator and the numerator, we can write this critical current density equation by different form. Here, the dF is the thickness of current, the ferromagnetic layer. This is nothing else, the volume of the ferromagnetic layer. Okay. And if you collect each material, each parameters in this form, we can easily find the physical meaning of each term. Here, this term is actually the volume, and volume multiply the unelastic energy divided by thermal energy is nothing else but the thermal stability factor called the delta. That is the very important data retention. I'm going to explain it next class more. But anyway, this is the energy barrier. This is thermal energy. To obtain the stable data storage, the energy barrier between two state, here is upstate, here is downstate. We need large energy barrier compared to the thermal energy. If this barrier is smaller or the comparable to the thermal energy, what happens is they can be tunnel each other. So it means we're gonna lose our store the information. So the switching probability by the thermal energy is exponentially proportional to the delta. So data storage society requires a certain number of the delta called the 60 for 10 years data retention guarantee. Maybe it depends on the detailed number, but usually the requires 30 or the 40 or 60 something to satisfy the data stability. So this is the kind of fixed number. How about this? This is a really physical constant. We cannot change anything. We cannot touch anything about this. And how about the KBT? We are living in a room temperature, or even higher temperature for the device application. The real working temperature is usually higher than the room temperature. But somehow we cannot change this one. So what can you do? Only this term. Here, the alpha is the damping constant of the ferrite layer, and P is the polarization of the spin polarization of the ferrite material. So typical value of the alpha, if set this one, we can easily calculate this value because this is the physical constant, this is required 60, and if we put the 300 Kelvin, this is the unit of the ampere. Because look at this, this is the dimensionless because the energy divided by energy, and KBT is the unit of energy. And if you consider the Planck constant, which one is joule per sec, joule sec. So if you multiply this one, then the remaining dimension is sec, the time. And we have a charge here. So charge divided by sec means the ampere. So we have a current unit. And this is generate certain number of the 1.5 milliamps. This is the value we cannot change it. So what you can do for the materials, we can change this number as small as alpha and as large number of the polarization, but the typical value is something here. So the required switching current for the STT NAM is cannot be smaller than the 30 micron, and typical order is order 100 microampere. That's the one of the problem. That is the little bit larger than the desired value. Actually, this value is smaller. This value is getting better and better, but unfortunately, there is some kind of a limitation of this critical current. Okay. Even though we can shrink down the cell size, if we shrink down cell size, what happens is it looks like by keeping the critical current density, because they are not depends on the area or the size of the cell. But once you shrink down the dimension of the area of the cell, we need keep this delta value for the data stability. So that means we need a higher analytic energy. means if we have a high analytic energy, we have to increase the JC. That is the general, maybe not general, but in usual case, in the engineering problem, if you want to solve some certain way, then we can improve this property. But sometimes this improvement of this property will decrease the other properties. So always there is some trade-off. So that's the difficult part for the engineering in many applications. There is no the best way. If you keep going for this way, then every property is getting better. Yeah, that cannot be happens in our real life. Yeah, maybe that's why we can get the salary from the company. The engineer got a job in a company. Anyway, so please keep in mind this idea. Okay, so we obtained this by solving this differential equation. We only talking about the k value that is corresponding the time-dependent behavior of the ML, the magnetic moment, right? We solve that the imaginary part is corresponding to the precession frequency, and the real part will determine the damping or the switching. And what we can do is, as I said, this is the kind of eigenvalue problems, and the k value is kind of the eigenvalue of the system. And what's the meaning of this magnitude, m0x and m0y? From this equation with the proper eigenvalue, we can obtain the ratio between the m0x and m0y. This magnitude is corresponding the magnitude of the magnetic radiation motion for the x direction and the y direction. So if you insert this one, we can obtain this result. So this is actually eigenvector. Okay, and if you put it back to the more our common equations, the k values, we have this very complicated form of the equation. But if you introduce more approximation, this is nothing else but the damping coefficient, the damping alpha with the frequency, damping frequency, and the numerator is also can be expressed more simple form here. And if you assume this term is smaller than this one, that is usually true, then we have this expression or this expression for the zero current and the small damping. So look at this. If you take a look at this equation again, and if you put it back, for the IMA case, and if we play with the films, we have a G direction in a film plane, and if we have a Y-axis, the orthogonal to the films, the M0S and M0Y ratio shows this number. For the y-axis is perpendicular, we have this form. But look at this. This is the just inverse. So what's the meaning of this guy? Yeah, if we have a certain external field, here the external field is pointing the minus direction. Anyway, so this and this is the kind of ratio of the field for x and y. Actually, this one is corresponding h here. We have a h external only. This term is the h plus ms term. So this case, if we pointing if you take a look the magnetic motion in front of this is y-axis, this is the say x-axis, and this is the G direction. So means if we have a mass station pointing this direction initially, and they make some rotation, elliptical motion, but the magnitude of the elliptical motion for the perpendicular direction is small, much small. But the in-plane motion is much more large. Why? Because they want to try to pointing to up, the dMAP fields will suppress the motion of perpendicular direction. So they have a such kind of elliptical motion. And this ratio is determined by this term. Because the MS is the source of the dMAP field. If we have a large MS, the making the perpendicular, the outer plane component costs more energy. For the PMA case, it's more simple. Yeah. PMA case, they found the circular motion because the ratio between the M0x, M0y is just a unit number. And this different, this plus minus I means the different phase. So they generate the circular motion. Okay. Yeah, that is also very important part for understanding the motion of the spins. So here, let's explain what's the difference between the field switching versus the STT switching. For the field switching, if we have a certain energy barrier, by applying magnetic field, we can making the barrier is getting lower, and finally they try to finding the lowest energy situation. That's the field switching. But the STT switching case, we didn't touch the energy barrier itself, but we can make the excitation of the spin direction energy, and finally they can make a reverse. So let's back to this equation again. I'm gonna explain one more things here. Here. Actually, if we have an external field here, and if we don't need STT, please look at this part. At this part. And okay, so just ignore this term and look at this part. Even though we don't have AJ, the spin torque, there is some chance this term can be positive. How you can do it? Making the negative number of this term. And look at this inside of this here, we have this form. And means if we external field is pointing the negative direction, there is a chance we can make the negative value of this one, and finally positive value of this one. And if you're including the NF energy, this external required field for the negative direction is actually exactly same as the Sturm-Alpers model. They should be, because they describe the same physical situation with the little bit different mathematics, but the result must be same. So you can find the Sturm-Alpers switching model, switching field in this the LH equations. Okay. And I'm gonna show some more example for the spin transfer torque switching by solving the LH equation. As I showed in previous class, we have a symmetric code, and all this material parameter is I already determined. Okay. Here you can find some physical constant, and now I set the zero external field. Here the external field is zero. This is zero. And the current is now I apply 0.3 milliamp. And this current density is corresponding, let's see. Yeah, this I current, maybe you can see. Yeah, just, can you see this number? Maybe it's too small. 이거 숫자 보여요? Can you see this number? This is the 1.3 something. So it's normalized current. So it's just 3% of larger than the critical current density. So let's solve this equation for, let's say, 10 nanosec. So it's gonna take a little bit time. If we are using desktop, it's much faster. Okay, here. You cannot see any motion of the moment. Yeah, there's nothing happens. But if you take a look the data, this column represents the theta polar angle. So they are starting from 0 and they are exponentially increase. But for the 10 nanosec, the magnitude is still 10 to minus 4 something. It's far away from the switching, but they are starting to switching. So let's increase the time. Okay, say 20 nanosec. Now, can see something here. Yeah, there is some point right here. This is what you obtained is here. Yeah, it looks like almost the same graph before. Should be different. Sorry. Hmm? Oh, yeah, here. Now we have almost 10 to minus 2 for the setup. But still, it's just 1 degree something. So let's increase a little bit more time. It's 30 nanosec. Okay. Now we got a switching. You can see the trajectory of the motion. Also, you can see theta motion. So it is, they are almost 0, but this is nothing as well. Exponential increase one. And it's pointing negative pi, the pi means they are pointing the down direction. Okay. And now we can find the switching take around 20 something nanosec, or around the 30 nanosec. So what's going on if we increase the current density a little bit more? Here we play with the 0.3 milliampere, but let's say 6. It's almost double of the critical current density. And I think we don't need this much time. Yeah. It's less precision and switching both fastly. So you can check it by taking the data. Yeah. You can see the shift occurred less than just few nanoseconds something. Very, very fast switch. And you can test many things with this simulation code, but here I have one question. in this solution, we just set the critical current. Can we obtain such kind of switching time in this equation? As I said, the real part of K, this is the real part of K, will govern the time-dependent motion. So, initially I showed the critical current is just 3% larger than the critical current density. So it means it's almost same this guy, and only some 3% remaining. So the K value is positive but small. So we have a motion of external exponential kt something, and they are very, very small, means it requires large number of the switching. But if you have a large K, means large current, then if you have a large K value, we need small t for the switching. Okay? So I'm going to explain that kind of time-dependent motion in next class with the thermal energy things. But yeah, the reason I'm focused on this STT switching is most of the modern spin transfer device is closely related to this spin transfer torque switching. Even though you are working sensors or just materials, you may need this technology. And also, this approach is general. As I mentioned, if we play with any kind of ground state with the perturbation, you can apply this idea. Okay? Yeah, today's lecture will stop here. And see you Wednesday.